What's really special about hummingbirds is that they can hover sustained. It's this tiny bird of only about 4 grams that can maneuver in ways that none of our airplanes can. So if we think about flight, it's actually quite simple. You have the weight of the animal, and that needs to be supported in the air by a lift force pointing up. Now, for a hummingbird, basically it's beating its wings 40 times per second. And this force is going to change all the time. And how does it keep control over this force? So if you think about this challenge of being able to hover still in the air and not move a bit, a direct measure of this force just doesn't exist. To study how birds fly and how they generate lift, you need a new instrument. It's only since last year, when my lab invented a new device, that we could directly measure the force that a bird is generating in flight.
On the day of my experiment, I go out to the field site on a remote location on the Stanford campus. I set up the hummingbird trap and then sit and wait for a hummingbird to come to it. Some days I catch one in 10 minutes, some days it takes like 5 hours. If it's healthy, then I'll take it out of the cage, give it some nectar from my hand so it has a full belly, and then I take it down to the experiment. I place it into the training box. First, it kind of flies around a little crazy. Then once it calms down, I put a stick inside and have it land on the stick. And I try to slowly bring the stick over to the feeder so it can realize that there's nectar in this little fake flower. Over each wing beat, the hummingbird has to generate the amount of lift force to equal its weight. One of the biggest questions about hummingbird flight is how much lift they generate in the upstroke versus the downstroke. We want to kind of quantify this. So once the hummingbird is trained, then we move it to the aerodynamic force platform experiment with all the high-speed cameras. The aerodynamic force platform consists of 2 force plates, one on bottom and one on top. And as the hummingbird is flying inside, it generates these pressure waves as it flaps its wing. And these pressure waves are transmitted at the speed of sound to the bottom and top plates. You get the vertical lift generated by the bird as it's flying. When the hummingbird leaves the perch and go to the feeder, I trigger the cameras so that they record data as it's flying. As the hummingbird is hovering, I'm recording the aerodynamic forces and the high-speed video from all 4 video cameras. So we have to rely on super high-speed cameras filming at 2,000 frames a second to isolate the wing as it's flapping in each wing beat. One of the most important things about flight is combating gravity. How do you generate lift to keep your body off the ground? If you stick your hand underneath a hovering bird, you can feel that pressure actually underneath. So we're measuring that pressure. The objective is to combine the aerodynamic force and the hummingbird wing movement to create a 3-dimensional model that quantifies exactly how the wing is moving as it's hovering.
One of the things that we can calculate is, for example, how much power it requires to hover. So if you think about a hummingbird wing, it's just beating back and forth, back and forth. And that costs a lot of energy. And the other thing that we found by modeling is that actually the amount of effort that has to go into accelerating and deaccelerating the wing when it's flapping at 40 times per second is unreasonably large. One of the exciting things that the research showed is that there must be some elastic storage mechanism that works like a wing attached with a spring, so that if the wing moves to one end, the spring pushes it back. This must be in place, otherwise it's going to cost so much to hover that it becomes unreasonable. One of the curiosities we have is what the mechanism is inside the bird that enables this elastic recoil. And one likely explanation could be a tendon. Another one could be a tendon-like function of the muscle itself. I think this modeling will show the most reasonable answer to how the recoil is achieved.
So one of the cool things about our experiment is it's so minimally invasive that we can capture the hummingbird in the morning, take a recording in the afternoon, and then release it once we get all our data. Every animal has something special you can learn from it when you dissect the biomechanics.
The way the research is going to be used in the future is we actually will understand better how a hummingbird stays placed in the air, but also to understand how hummingbirds reorient their force. And by better understanding this, we can then redesign small drones that also need to do the same sort of thing. Most people don't realize in what sort of special time we live. Technologically, there's just so much cool stuff you can do, and there's so many scientific questions. So I think we'll be very busy for a long time.